Miss Jody here on our next video for chemistry. Don't forget that we are continuing to take our notes while we're separated on half sheets to be glued into the journal. This is our last topic in our module 13, and then we will move on to module 14, which is kinetics, and then 15 is chemical equilibrium, and then 16 is oxidation and reduction. So we're almost there. As you see my background here, I have added a new color sheet for each one of the, weeks of our time separated. So we've been separated for 4 weeks of lessons here. So sad. I hope you guys are doing well, and I hope you're keeping up with everything, and I really hope we can get together in May and do some stuff, some fun stuff. I really hope so. If worst comes to worst, maybe early summer, early June before camp starts. Something. I don't want to just end this year and not be together and finish some of our experiments. That would make me so sad. But anyways, at least we're getting some work done during this time, hopefully. All right, so Gibbs free energy. Now this, finishing up the chapter, let me just flip back here. This whole chapter on thermodynamics. Now let's just stop right here. So our last videos, when we were talking about the second law of thermodynamics, obviously the first law of thermodynamics, energy cannot be created or destroyed. It can only change forms. And then we looked at the second law, the entropy of the universe must always either increase or remain the same. It can never decrease. And that's part of that being created or destroyed. So as this energy is moving out and spreading out, we talked about this idea of entropy, a measure of the disorder that exists in a system. And so it's obviously energy divided by moles and the temperature and all that. And so we talked about, like, say, for instance, this vase and how it's all put together, then you drop it into the small pieces, broken pieces. So this is more orderly. It's all together, broken in, then you break it into all bunch of pieces, more disorder, a higher entropy, and that entropy is only one way. You never see the broken vase jump back into the all put together vase, right? So we use that as an illustration of this entropy world, the measure of disorder, and how the disorder, when it comes to the second law of thermodynamics, and the entropy of the universe must always either increase, so you might have, or disorder must increase or remain the same. It can never decrease. It can never get more orderly. Even if it seems like it's getting more orderly, remember we talked about in the second video, or maybe I did them together, I don't remember, we were talking about entropy, and we were saying the proper application of the second law of thermodynamics is when you see something like water in its higher entropy, more disorder in its liquid state, but then when you freeze it, then it would be, truthfully, it would look as if it was that it was defying the law, the second law of thermodynamics, because when you freeze it, then it goes into a lower entropy, less disorder, because it's in its solid form. Because remember, the solids have less entropy than the liquids and the gases and so on. And so it would look as if we made it go from more disorder to less disorder, and so that it would be defying the law of thermodynamics, the second law of thermodynamics. But the truth is when the water freezes, remember that some of that that pulling out of the energy to make it turn into its ice form, is that energy is going into the surrounding around the ice cube, and so the surrounding is heating up. So we have to look at it as a whole, the system, what's happening plus everything around it. And so when we looked at this, you were supposed to do some of your practice problems here and then look in the book, and then on this one you were to do some of your practice problems and then look in the book and make sure they're right. And then we move on to continuing that thought with looking at Gibbs free energy. So Gibbs free energy, so if we think about the processes like chemical reactions and all this energy change, trying to keep track of it, where is it going, not just the enthalpy, where the energy in the system and then that changing, but then even the entropy, like we just talked about, the disorder, how more disorderly it gets and not. And so we're keeping track of all that. So if a process is to occur, that means like a chemical reaction or whatever, it must result in no change to the entropy of the universe or an increase in entropy of the universe. So remember, we were just talking about this with the law of thermodynamics. So if it's actually going to occur, it must result in no change to the entropy. It means zero. It's adding zero change to entropy of the universe, or it must increase the disorder of the universe to keep consistent with the law of thermodynamics. So what do we say? The law of thermodynamics. Nothing can get less disorderly. So what would that be? Nothing can, our universe is constantly leading towards disorder and energy spreading out. It's not going the opposite way where things are getting more orderly. So there has to either be no change in the entropy, no change in the disorder, or it has to increase the disorder. So increase the entropy. So if a reaction is really, a process is really going to occur. So when we look at that, we say entropy of the process. What's that talking about in this? Well, that's the entropy of the chemical reaction, the change in entropy, the change in disorder. So what's the change need to be? It needs to be no change to the entropy of the whole universe, the whole system, or an increase in it. So it's got to become more disorderly. So the entropy of the process is the change in entropy of the chemical reaction. And then we also have the entropy of the surroundings. We can't forget that, like the freezing water. There's also the change in the surroundings that has to be taken into account to keep all this balanced with the law of thermodynamics. So if the water freezes, it looks like, oh, we were able to make it go the wrong way. And I thought you said its entropy is a one-way ticket. You got the vase and it breaks into little pieces, and the little pieces never jump back into the vase. It looks as if we created a more orderly system from our liquid to our ice. But if we take into consideration the change in the surroundings. Now, when you have the change in surroundings, the entropy of the surroundings, what you're really looking at to help you figure that out is the change in enthalpy. Remember, we studied the change in enthalpy. It was whether the energy in the reaction was released in an exothermic reaction or whether the energy was absorbed in an endothermic reaction. So when we're looking at these two, they can help us understand if the process is actually going to occur, if it's actually going to be in line with the second law of thermodynamics. And so that's where the world of Gibbs free energy comes in. So Gibbs free energy, this is a new formula. So you have the change in the Gibbs free energy, which is going to be the G here, is equal to the change in enthalpy of the reaction. Okay, so we're thinking of the reaction, the change in enthalpy, so we know what the changes are, either exothermic or endothermic, minus the temperature of the reaction during the reaction, multiplied by the change in entropy, the change in the disorder. So when we look at this, this can tell us whether or not a reaction is consistent with the second law of thermodynamics. Because here's the thing. If it is consistent with it, meaning what we see that law to state, that the universe, when it comes to entropy, the change in entropy of the universe, it needs to have no change or it needs to increase. So either no change in the order or more disorder. Everything is moving to more disorder in the system. And so if it is consistent with that, we will call it a spontaneous reaction. And so spontaneous means it can proceed. It means it's in line with the law of thermodynamics. It's working. And that will be seen in a negative. If your number for your Gibbs free energy in the end is negative, then it's going to be something, because remember, it's got to no change, or the entropy's got to increase. It has to be positive. If it's positive, it isn't. Or I'm sorry, positive will be if it isn't consistent with the law of thermodynamics, we call it not spontaneous. And that means it cannot occur. So some reactions cannot occur at, like, say, certain temperatures. You try to do a reaction and you can't get it to happen. But if you change the temperature, and so therefore changing the thermodynamics side of it on where the energy is and who has it and where's it going and how much is in the system, you can get certain reactions take place. That's why sometimes when they're doing chemical reactions, they might say something like, oh, you this reactant with this reactant under add intense heat or something, because sometimes you need different temperatures to actually get these things to happen. And so when it comes to figuring out Gibbs free energy, the book does note that this is an approximation only. So what that means is that there are other ways that a reaction can affect its surroundings other than through enthalpy. And so our book says we're not going to go into those details unless you take advanced chemistry, but the idea is we have to remember when we're doing some of these calculations, they are approximations only, like approximately figuring out whether the reaction can take place spontaneously or not spontaneously, depending on the situation, and whether it would be in line with the second law of thermodynamics or not. Okay, now with that, the change in Gibbs free energy, we realize that Gibbs free energy is a state function. Remember what a state function is? Means no matter how you got to that conclusion, what path you take when trying to calculate it, you still get to that same conclusion in the end. Like they gave the example of, no matter if you're on your way to the fair, if you took the back roads or you took the highway, you still got to the fair and had the same amount of fun. So the fun is the state function. It doesn't matter how you got there, it still happened. And so when it comes to Gibbs free energy, it's a state function. And just like the other state function that we were talking about, there is the idea of what's called the standard Gibbs free energy of formation. Remember, we looked at this and we had charts on the standard enthalpy of formation measured in kilojoules per mole. And remember, you could just look at the chart and you could use that when we started looking at Hess's law. And it's kind of, I don't want to say a shortcut, but once we figured out that there are certain, under standard conditions, you have the standard enthalpies of formation, and you can use those, as long as you know the states of what the substances are in, to calculate some of these things that you're looking at using Hess's law. And then there was also when it came to entropy, we had the standard absolute entropies, and that was represented with the S with the little degree sign, meaning standard conditions and standard, which the standard conditions was the standard temperature and the standard atmospheric pressure. And that was measured in joules per mole times Kelvin. Okay, so just like these standard enthalpies and the standard absolute entropies, we can have the same thing in the Gibbs free energy, the standard Gibbs free energy of formation. And that's this little delta, the change in Gibbs free energy with a little f for formation and the little symbol with a degree symbol for standard conditions. And that will be measured in kilojoules per mole. All right, so when we start looking at the Gibbs free energy and using this, it's noted that using the change in Gibbs, or the standard Gibbs free energy of formation, with Hess's law, we can calculate the standard Gibbs free energies. And so with Gibbs free energy of formation, standard conditions, no, the Gibbs free energy under standard conditions, putting this in Hess's law is equal to the summation of the change in the Gibbs free energy of formation, standard conditions, of the products minus the summation of the change in the Gibbs free energy of formation of the reactants. That's a mouthful, right? So when we look at the change in the Gibbs free energy of formation of any element in its elemental form is 0, as it is with the change in enthalpy of formation. Now remember, we had a little change there when we talked about entropy, but with enthalpy, any of the elements, which was just the element itself, like hydrogen by itself or whatever by itself, or the atoms that are homonuclear diatomic, when it came to their number, it was always 0. But then when we went into entropy had we had to make sure that we noted, because when we looked at entropy and we were putting it kind of in the Hess law form, if you remember, when it came to entropy, it was similar to Hess's law, except the entropy of an element is not 0. So if you have to try to keep it straight, you say, okay, when it comes to enthalpy, the elements are 0, and they're homonuclear diatomics. They're standard form or whatever is 0. But when it comes to entropy, it is not 0. But then when it comes to Gibbs free energy again, because if you look at both of these, the Gibbs free energy and the enthalpy, see how they enthalpy, the standard enthalpies of formation, see they're in kilojoules per mole. And then with the Gibbs free energy of formation, standard is in kilojoules per mole. See how they're both in kilojoules per mole? And these both are the two that the element or the homonuclear diatomic by itself is 0. But this one, the standard absolute entropy, see how this is joules per mole times Kelvin? So that's kind of a way to remember. These two that match in their units are the ones where the elemental form is 0. So the amount of energy in the elemental form, 0 of the standard enthalpies, and then the element form in the Gibbs free energy, 0, but not in the standard absolute entropy. So not in the entropy world. So in the enthalpy and the Gibbs free energy, enthalpy and Gibbs free energy, those two, the elements will be 0, or the homonuclear diatomics. But in the entropy, no. So hopefully that helps, because this stuff gets all confusing after a while. Oops, what am I doing? All right, so keeping that in mind when we're starting to look at how to calculate these, so trying to use the change in the Gibbs free energy of formation, standard there, with Hess law, we can calculate the standard Gibbs free energies. So we use our formula, like I just stated there, and then if there happens to be any element in the equation when we're adding up our products or adding up our reactants, we have to remember that its elemental form, it's 0, as it is with the change in enthalpy of formation. Okay, so standard conditions, just as a reminder here with this particular Gibbs free energy, standard conditions, 298 Kelvin and 1 atm of atmospheric pressure, right? So that's standard. So if say you're doing a reaction and it's not at standard conditions and with the standard temperature and the standard atmosphere, well, then you can't use this little easier summed up version of like Hess's law. You have to use the whole equation. So looking back over here with this equation, which is the change in Gibbs free energy is equal to the change in enthalpy minus the temperature times the change in entropy. You got to use that whole equation if you don't have your standard conditions. But if you do have your standard conditions, then just like Hess's law made it a little bit easier, you can use this particular equation. Okay, so let's do the first one, and then the other two I'll have you do on your own. So with this one, it says, okay, we had already calculated the enthalpy, the change in enthalpy of this reaction and the change in entropy of this reaction. So it says, okay, there was your reaction. What is, and this is your change in enthalpy, which is negative 114.2 kilojoules. And then it said this one, your change in entropy is negative 147 joules over Kelvin, the temperature. And so it says, what is the change in Gibbs free energy? And that's what basically with Gibbs free energy, it's relating those two, right? So it's relating those two products together. So what is the Gibbs free energy at 532 degrees Celsius, which is also 805 degrees Kelvin? Is it spontaneous? Is it a spontaneous reaction at room temperature? Okay, so what they want you to do is to figure it out. And obviously you have to figure out, can you use this Hess law world here, or do you have to go back and in order to relate these two, do you have to go into the Gibbs free energy regular formula here? Well, we know that we do not have the standard conditions, right? And so when we look at the situation, we have 805 degree Kelvin, and so we're going to be going just to the regular formula there. And so we have the Gibbs free energy, or change in Gibbs free energy, is equal to the change in enthalpy, which we already have because the change in enthalpy is negative 114.2 at standard conditions. And then subtract the temperature. So which temperature am I going to use? Am I going to use 532 degrees Celsius, or am I going to use Kelvin? Well, the fact that I'm going to be relating the temperature to the change in entropy, and when you have the change in entropy, when we look at the entropy world, if you remember, I could flip back there, but this kind of shows you a little bit down here, the standard absolute entropies. See how they're calculated in joules per mole times Kelvin. So we're at a Kelvin situation when we're relating the entropies. So we're going to keep that consistent there. So we're going to use 805 degree Kelvin, or 805 Kelvin. You don't say degree, but I don't think you say it. But multiplied by the change in enthalpy. What's the change in enthalpy? Well, the change in enthalpy is negative 147 joules per Kelvin. But the problem is you can't mix these two, joules versus kilojoules. So this one's going to have to be converted, and that's where this little arrow leads us down to. So here's the conversion. So 147 joules over Kelvin multiplied by 1 kilojoule. 1 kilojoule is equal to 1,000 joules. So I'm multiplying this conversion here. This is my conversion factor. 1 kilojoule equals 1,000 joule. Then I multiply that, and that equals negative 0.147 kilojoules per Kelvin. Okay, so my joules would have notched out here, both of these matching, and I would just have kilojoules at the top and Kelvin underneath it. Okay, so now I can add that to my change in entropy. So then when I do this calculation, really easy, I'm gonna do my multiplication first. So I'm gonna put these inside just so we have the multiplication here. Make sure that so that negative sign is not part of this, or that subtraction. So I have 805 Kelvin times negative 0.147 kilojoules, and that, let me look, was it came to negative 1.18, and it was like 335. So then I was trying to keep the significant figures to the mole world, which was change in enthalpy, and the enthalpy world is kilojoules per mole. So I was sticking with these four right here for significant figures. So 118.3, I think, is where I was going with. I think I was keeping that. And then, so that was the answer to that one. And then I just continue on. So minus 114.2, subtract, and this is negative. So negative 114.2 kilojoules minus negative 118.3, and that equaled 4.1 joules, I think, or whatever. In the book gives us 4 kilojoules. Okay, and so that was my calculation. And so it says in the book, notice that the change in entropy has the Kelvin temperature, which we did. So we made sure that because this had the Kelvin, we put the Kelvin in there, so we didn't get that mixed up. And then the decrease in entropy of the reaction is not offset by the increase in entropy of the surroundings caused by the release of heat, right? So since the change in Gibbs free energy is positive, we can say that the reaction is not spontaneous. And so remember when I said, because this is positive kilojoules over here, when I said if it's negative, then it's going to be in line with the law of thermodynamics for it to be spontaneously happening at the, on its own. And then, so if it is, then it is going to be, but if it's positive, then it's not spontaneous and cannot occur on its own without changing something. Okay, and so then we have the next two questions, which I just wrote out for you, and then you can work through these in your book, and they are on page 479 and 480. And it's continuing relating what we just did. Is there any temperature at which the above reaction does become spontaneous? And so that's the same reaction that we just did here. And so you look at this reaction and say, okay, well, it didn't become spontaneous, but what if there is a change in temperature? Could we change the temperature and it become a spontaneous reaction, a balanced out, not defying the law of thermodynamics by being either zero in its entropy or increasing in its entropy? And so I gave you this start here so you could try to see if you could do it without looking in the book. So what they're trying to ask you is, so your change in enthalpy, because it says, is there any temperature at which the above reaction does become spontaneous? So you would take your change in enthalpy minus your temperature multiplied by your change in entropy, and your goal would be for all this to become less than zero. Because remember, we wanted it to be negative. It's got to become a negative number. At this point, it is a positive number. So in this positive situation, like we said over here, then it is not spontaneous. It cannot occur. So we need to change something. And so if we change the temperature, would that help? And if so, what would that temperature be? So what we're trying to figure out is calculating, is there a way for changing this temperature to get this number to be zero? And if it is, and we can get that number to be, zero or less than, then this could become a spontaneous reaction. So you're going to use those numbers before to try to figure it out. And then the last one is using a calculation where things are at standard conditions. So you could use the Gibbs free energy with Hess's law. So what is the change in the Gibbs free energy for the following reaction at standard conditions? So there's your key that you can use the little easier version that uses the charts. Is it spontaneous? The question is, and here's your reaction. So you look at your reaction and use the chart in the book, and the standard Gibbs free energy of formation, the chart that they have is on page 478. So use that chart, put it in there, and not forgetting that things like in their elemental form are going to be zero. So remember, you're going to calculate, you're going to add up the reactants, add up the products, put them in the Hess's law, and figure it out with the chart. Okay, so do those two and see how you do, and check your answers on page 479 and 480. And then send me a picture or something. I want to see how you're doing. Make sure you do all your work on this. And I'll, and this is actually the last one for our module. So yay, yay, yay. Move on in our next video to kinetics.